Welcome all. This is lecture number 7. In this lecture, we will discuss Stokes theorem. Stokes theorem means relation between line and surface integral. So the question arises, what is Stokes theorem? What is the statement of this theorem? So Stokes theorem is also known as Kelvin-Stokes theorem. After Lord Kelvin and George Stokes, the fundamental theorem for curl, or simply the curl theorem, is a theorem in vector calculus. Given a vector field, the theorem relates the integral of the curl of the vector field over some surface to the line integral of the vector field around the boundary of the surface. The classical Stokes theorem can be stated in one sentence: the line integral of a vector field over a loop is equal to the flux of its curl through the enclosed surface. Now see, in this particular figure, this is a three-dimensional figure. Here C is a curve and S is the surface where we take a small part ds, where this is the vector f and it is unit normal vector n cap. Then its image lie in this particular manner, it is dx and dy. Then mathematically Stokes theorem can be stated as circular integral vector f dot vector dr is equals to double integral s curl vector f dot n cap ds, where n cap can be stated as cos alpha I plus cos beta j plus cos gamma k. This is a unit external normal to any surface ds. This is the example 1. Evaluate circular integral C vector f dot vector dr by Stokes theorem, where vector f is equals to y square I plus x square j minus x plus z k, and C is the boundary of the triangle with vertices at 0, 0, 0, 1, 0, 0 and 1, 1, 0. So to solve it, we have first curl vector f can be stated as del cross vector f, and it can be represented as in the determinant, where the first row represents the I, j, k, second row del over del x, del over del y and del over del z, and in the third row we have the coefficients of vector f, that is y square, x square and minus x plus z. Now we have to extend it or expand it. So when we expand it through I, so first row, first column, both are leave. So minus x plus z, when we differentiate partially this minus x plus z with respect to y, then the differentiation is 0, and minus a differentiation of x square with respect to z is also 0. So the component of I is 0, and then minus j, we have to leave first row and second column. Then partial differentiation of minus x plus z with respect to x is minus 1, and partial differentiation of y square with respect to z is 0. So it will be minus is already there and 1 minus is from there, so minus minus plus j. And same as for the third case, leave first row and third column. Then partial differentiation of x square with respect to x is 2x, and partial differentiation of y square with respect to y is 2y. So we can take 2 outside, so it will be x minus y k. So this is the value of curl. Now draw this particular triangle. So it is here we are seeing that there are three coordinates. So it is a three-dimensional. So make a three-dimensional image. Let this is x, y, and z. Now the first vertex is 0, 0, 0. So it lies at the center. Second is 1 is 0, 0. So it means it represents the x-axis, and the 110 lie in the xy plane. So just like this. So taking this A and this point B, so the coordinate of O are 0, 0, 0, coordinate of A are 1, 0, 0, and coordinate of B are 1, 1, 0. So the equation of this line is basically x-axis y equals to 0, z equals to 0, same as the equation of OB. It will be, it is in the xy plane, so 0, 0 and 1, 1. So the equation of line passing through 2 points. So from this we can get it y equals to x. So by the Stokes theorem, circular integral C vector f dot vector dr can be represented as double integral s curl vector f dot n cap ds. So curl of vector f is given already here, j plus 2 minus 2x minus y k dot n cap. N cap will be, now see this is the xy plane, so the z is equals to 0, so n cap will be k cap, and ds will be converted into dx dy upon mod of k cap dot k cap. So k cap dot k cap 1, and when we make dot product with these two brackets, then it will be twice of x minus y dx dy under the limit. Now see the limits are, when we draw strips parallel to y axis, then at this particular point y equals to 0, and at this point y equals to x, and the limit of x are 0 to 1. So the limits are, we can take this twice outside. So integral x equals to 0 to 1, integral y equals to 0 to x, x minus y dy dx. So first we have to integrate this with respect to y. So the integral of x with respect to y will be xy, and the integral of y is y square by 2 under the limit 0 to x. So on putting the limits, when we put y equals to x, then it will be x square, and it is x square by 2. So x square minus x square by 2 will be x square by 2, and when we put 0, then entire function will be 0. So it will be x square by 2, and by 2 is cancelled out, this denominator 2. So the function remains integral x equals to 0 to 1 x square dx. So the integral of x square is x cube by 3 under the limit 0 to 1. So on putting the limit, we get the value 1 by 3. So the circular integral C vector f dot dr for the given function is 1 by 3. Now moving on to the next example. Example 2. Verify Stokes theorem for vector f equals to y minus z plus 2i plus yz plus 4j minus xzk over the surface of the cube x equals to 0, y equals to 0, z equals to 0, x equals to 2, y equals to 2, and z equals to 2 above the XOY plane. Above the XOY plane means open at the bottom. So to solve it, first we make the cube. Now this is the cube. Let this is A, B, C, D, E, F, and this is G. Now the coordinate of O is This is the origin. So 0, 0, 0. Coordinate of A are 2, 0, 0 because it is given here. Coordinate of C 0, 2, 0. Coordinate of F 0, 0, 2 because it lies on the Z axis. Now coordinate of B, it is in the XY plane, so 2, 2, 0. Coordinate of E in the YZ plane, so 0, 2, 2. Coordinate of G, it is in the XZ plane, so 2, 0, 2. And coordinate of T, it is in the all three planes, so 2, 2, 2. Now we consider the surface of a cube S1 in the figure, and bounding path is O, A, B, C, O, this particular path, which is shown by the arrows. Because we have to verify Stokes theorem, so to verify it, we first solve the problem with the help of line integral, then solve the problem with the help of surface integral, and the value so obtained from the both case or both method should be same. And if it is same, then we can say Stokes theorem is verified. So for the line integral, we can say integral C vector f dot dr. First integral C, this is the vector f, y minus z plus 2i plus yz plus 4j minus xz k dot product with vector dr. It comes from vector r and the value of vector r is xi plus yj plus zk. So the vector dr is equals to I dx plus j dy plus k dz. So when we make dot product of it, then I dot I, j dot j, k dot k will be 1, rest are 0. So it will convert into integral C y minus z plus 2 dx plus yz plus 4 dy minus xz dz. Now integral C vector f dot dr can be represented because we are taking this bounding path O, A, B, C, O. So the line integral will round through the line. So circular integral for OA plus 4 AB plus 4 BC and plus 4 CO. So circular integral C vector f dot d vector dr can be represented as for the line OA, this particular line. This is the x-axis. So at this particular case, at the x-axis, y and z both are 0. And if y and z are 0, then dy and dz both are 0. And the limit for x are 0 to 2. So x equals to 0 to 2. Now put here y 0, z 0. So only 2 dx remains. Here yz 0, dy be 0. Then this is also 0. Same as dz 0. Then this is also 0. So only 2 dx remains in case of OA. And the limits are only for x. So initial limit is 0 and the boundary limit is 2. So the x equals to 0 to 2. Now in the case of AB, this lies in the xy plane. So in this particular plane, z is equals to 0 and x is a constant, that is the x equals to 2. So the dx is equals to 0 and dz is equals to 0. So on putting here dx is 0, then this function 0, dz 0, then this function 0, z is 0, then the yz is 0. So only 4 dy remains and the limits are for y. So the initial limit for y is 0 and the end limit is for y is 2. So the limits for y are 0 to 2. Now the case for BC, it is also lie in the xy plane. So in this particular case, z is equals to 0 and the y is equals to 2. So the y equals to 2, so the dy is equals to 0. And since z equals to 0, then the dz is also 0. So see, dy 0 and dz 0, then these two terms are 0. So only this is equals to, this is remains, and y is equals to 2 and z is equals to 0. So 2 plus 2 is 4. So it will be integral 4 dx and the limits are for x. So in this particular case, at this particular point x is equals to 2 and at this particular point x is equals to 0. So the limits for x are 2 to 0. Now the CO lies on the y-axis. So in this particular case, x and z both are 0, and when x and z is 0, then dx and dz both are 0. So putting here dx and dz both are 0, xz is 0, so only 4 dy remains, and in this particular case the limit for y is at this particular point 2 and at this particular point is 0. So the limits for y are 2 to 0, 4 dy. So now integral of 2 dx is 2x under the limit 0 to 2. Limit of 4 dy is 4y under the limit 0 to 2. Limit of 4 dx is also 4x under the limit 2 to 0, and same as 4y under the limit 2 to 0. So now when we put limit x equals to 2, then 2 to the 4, y equals to 2 to 4 to the 8, x equals to 0, 0, x equals to 2 to minus 2, minus 2 for the minus 8, and same as here minus 8. So it is equals to minus 4. So this is the value of the function by the line integral. Now moving on to the surface integral method. So now see, this is open at the bottom, so it is a 6 faces cube, so it will have only 5 faces. This face OABC will left, so only the face ABDG, BCED, OCEF, FGDE and OAGF remains. So we have to find the value for these 5 faces leaving the bottom face, that is OABC. So for the surface integral, we first find curl vector f, which is equals to del cross vector f and can be represented in the determinant. So ijk del over del x, del over del y, del over del z. Component of I y minus z plus 2. Component of j in vector f is yz plus 4. And component of k in vector f is minus xz. So now expand it through first row. So for the I, when we find partial differentiation of minus xz with respect to y, it will be 0, and partial differentiation of yz plus 4 with respect to z, it will be y, so it will be minus yi. For the j, partial differentiation of minus xz with respect to x will be minus z, and partial differentiation of y minus z plus 2 with respect to z is minus 1, and minus is already there, so it will be plus z minus 1 j. And for the k, partial differentiation of yz plus 4 with respect to x is 0, and partial differentiation of y minus z plus 2 with respect to y will be 1. So it will be minus k. So the value of curl vector f is minus yi plus z minus 1 j minus k. Now for the 5 faces, double integral s del cross vector f dot n cap ds can be defined as double integral for DEFG plus double integral del cross vector f dot n cap ds for OAGF plus a double integral del cross vector f dot n cap ds for BCED plus a double integral ABDG and plus double integral for OCEF. Let it is equation number 1. Now we have to find value for each 5 cases. So first, for double integral DEFG del cross vector f dot n cap ds is equals to double integral for DEFG, putting the value of del cross vector f is minus yi plus z minus 1 j minus k. dot product with, now see, this DEFG lie in the XY plane. So for the XY plane, Z is equals to 0, and when it is equals to 0, then the n cap will be k cap. And now it is in the forward direction, so it is k cap. So the ds will convert into dx dy upon mod of k cap dot k cap. This concept we already discussed in the lecture of the surface integral. So when we make dot product with these two brackets, then it will be -1 dx dy. So for the limit x equals to 0 to 2, y equals to 0 to 2, dx dy. So first integrate with respect to x, then the dx will be x under the limit 0 to 2, so it will be 2, and again integrate with respect to y. So the integral of dy is y under the limit 0 to 2, so it will be 2, and 2 already there, so it will be -4. So this is the value of double integral DEFG del cross vector f dot n cap ds. Now for the second case, double integral OAGF del cross vector f dot n cap ds. So it is double integral for OAGF, same as vector f is minus yi plus z minus 1j minus k cap dot minus j cap dz dx upon mod of minus j cap dot j cap. So it is in the xz plane, basically in the left direction. So when this is in the xz plane and in the left hand direction, then we take j in term of minus j. So when we make dot product, then it will be minus z minus 1, it will be 1, so minus z minus 1 dz dx, and the limits are z equals to 0 to 2, x equals to 0 to 2, but there is the variable in the z. So first we integrate it with respect to z, so the integral of z is z square by 2, and integral of 1 is z under the limit 0 to 2. So when we put a limit z equals to 2, then it is z square, that is 2 square, which is 4, and 4 by 2 is 2, and minus 2, so it will be 0, and when we put 0, then it is also 0. So the entire function is 0, and when the function is 0, then the entire integral will also 0. So the value of double integral del cross vector f dot n cap ds for the phase OAGF is equals to 0. So we get value of the two surfaces. Now for the surface BCD del cross vector f dot n cap ds can be defined as double integral BCD. This is the vector f minus yi plus z minus 1j minus k cap dot j cap. Now it is in the xz plane, but in the right hand direction. So when it is in the right hand side, then n cap will convert into j cap. So j cap and dz dx upon mod of j cap dot j cap. So it is 1, and the dot product of these two function will be z minus 1 only. So double integral for the surface OAGF z minus 1 dz dx, and the limits are 0 to 2, 0 to 2. So we can write it in a manner: integral 0 to 2, integral 0 to 2 z minus 1 dz dx. Now this is the same function which we discussed for the previous phase. So the integral of z minus 1 is z square by 2 minus z under the limit 0 to 2, and when we put limit, then it will be 0. So the value for this particular surface double integral BCED will be 0. So now moving on to the next surface. Next surface is OCEF. So the double integral for the OCEF del dot cross vector f dot n cap ds is equals to double integral for the surface OCEF minus yi plus z minus 1j minus k cap dot minus I cap. Why minus I cap? Since OCEF is in the YZ plane. In the YZ plane in the backward direction. That's why we take minus I here. So minus I in place of n cap, and it is mod of minus I cap dot I cap. So it will be 1, and when we make dot product, then it will be minus y dot minus yi dot product with minus I, so it will be y. So we can write it as y dy dz. So the limits are y equals to 0 to 2, z equals to 0 to 2. So we can write it in a manner. So the integral of y is y square by 2 under the limit 0 to 2. So on putting the limit, 2 square is 4 and 4 by 2, that is 2. So it will be twice integral 0 to 2 dz. So the integral of dz is z under the limit 0 to 2. So when we put limit, so again 2 arises and 2 to the 4. So this is the value. Now moving on to the last phase. So double integral for the phase AB dg del cross vector f dot n cap ds can be defined as double integral for AB dg. Vector del dot vector f is minus yi plus z minus 1j minus k cap dot I cap. N cap is the I cap because it is in the yz plane in the forward direction. So for the forward direction it will be positive, and the ds will convert into dy dz upon mod of I cap dot I cap. So this function will convert into minus y dz dy, and the limits are same as 0 to 2, 0 to 2. So minus integral 0 to 2 integral 0 to 2 y dy dz. So the integral of y is y square by 2 under the limit 0 to 2. So performing same as we done in the previous. So it will be minus 2 integral 0 to 2 dz. The integral of dz is z under the limit 0 to 2. Again 2 arises. So minus 2 into 2 is minus 4. So now we have value for the all 5 phases. So putting all values in the equation number 1, we get double integral as del cross vector f dot n cap ds is equals to minus 4 plus 0 plus 0 plus 4 minus 4. So it is equals to minus 4, and the value comes from the line integral is also minus 4. So the value from the both method is same. So we can say double integral as curl vector f dot n cap ds is equals to circular integral vector f dot vector dr is equals to minus 4. Hence we can say the Stokes theorem is verified. So hope you enjoyed this particular lecture. We will meet in the next lecture. Thank you.